Alright, hello everyone and welcome again. So in the last video we learned how to find the area highlighted by this green color and purple color regions. Actually it's a one region, but in the last problem we learned that we had to divide the entire region into two parts and then had to set up in two integrals separately and then add them up, and then we were able to find the area, right? Okay, so now we're going to look at this problem in a different way. So let me draw that graph again. So this is square root x plus 2. This is y is equal to x. This is going from -2 to 2. Right. Now, so the reason that we had to do that was that this entire region has two separate regions, right? Like this is the region 1 and like this is the region 2. Now, here's another way to tackle this problem. So in numerical approximation lesson, we learned that when we try to understand where the integral, the idea of definite integral coming from, we learned that it's coming from like when you have to find the area under a curve, we separate the x-axis into several regions, we partition the x-axis, right? And then we form these rectangles, right? Vertical rectangles, right? So that's how we try to understand the definite integration, right? Try to derive the definition of definite integral, right? So the basic idea is we use the x-axis and we call this delta x, okay, right? The width, and then we set up the rectangles vertically. Now here's a different way to think about this. Rather than setting up those rectangles vertically, what if we divided the y-axis instead? We divide the y-axis into several parts. That means what we partition the y-axis, and instead of the width being delta x, it's going to be now delta y, and we are going to use horizontal rectangles to find the area, okay, under a curve, right? So we can do the same, no problem. We can use that technique. So we are going to use that technique to find the area in this region. Check this out. If I set up horizontal rectangles, now check this out. If I connect, okay, all the way, I am always going between the same two graphs. On the left, I am touching square root x plus 2. On the right, I am always touching y is equal to x. Check this out. If I draw some horizontal lines, the left is always touching square root x plus 2 and the right is always touching y is equal to x. That means if you think about this in that sense, if you think about this region, entire region in that sense, through these horizontal lines, you only have one region. You don't have multiple regions. Okay, I want you to understand this. All right. So check out this. If you think about vertical rectangles like this, see here it's top touching square root x plus 2, bottom x-axis. But here's top touching square root x plus 2, but here y is equal to x line. Now that's why we have two regions. This is the first region, this is the second region, right? But if you think about through the horizontal lines, you can see it's always left touching square root x plus 2 and right y is equal to x. Okay, so now if you think about this with horizontal lines, you only have one region, no two regions. That means you can set up one integral, okay, thinking about these horizontal lines and find the area, rather than breaking it up into multiple regions and finding the area. Okay, so that's the idea. So that means we are setting up the integral in terms of y now, not x. Okay, so now we are dealing with delta y. Now the idea is same. Okay, so when you're setting up the integrals with respect to y, okay, here's how you do it. With respect to x, we took the top function minus bottom function. Now how about when you're thinking about y? Well, it's the function on the right minus function on the left. So it's x minus square root, So it's the function on the right minus function on the left. Okay, so we have to be careful. I almost made a mistake here. So y function on the right minus function on the left. So if you think about this horizontal rectangles, you can see this is like the top part of the horizontal rectangle, and this is like the bottom part of the rectangle. Okay, so let's do this slowly. I was trying to get ahead of myself. So now you're setting it up with respect to y. So you're integrating with respect to y. Okay, you're setting up an integral of y. Now see delta y. So your change is delta y. So here dy. Now you have to think about the limits of y. Okay, not limits of x now. So y is going from 0 because the smallest y value is 0. The topmost y value is, you have to find that out. So when x is equal to 2, what's y? Y is also 2, right? The top value. So y is also 2. So this is 2. So now you are thinking about the limits of y, not limits of x. Now the right hand side function. Now you have to write it in terms of y. Okay. So remember, I think I wrote it as x minus square root x plus 2. This is wrong because now we are setting up the integral in terms of y. Okay. So the rightmost function is y. Y is equal to x. So the function is y. Now the leftmost function is, what you have to do is you have to make x subject. That's what you need to do. Here automatically x was subject, so x is equal to y. So to make x subject here, you have to take this square. So y square is equal to x plus 2. So x is equal to y square minus 2. That's the function in terms of y. So you need to write the function in terms of y. Okay, so you need to make x subject. So it's minus y square minus 2. This is the integral that will give you the area of this entire region. Now see the difference. In the previous video, we had to divide the region into separate parts to get an integral representation using x. Okay, when you do the rectangles vertically. But if you switch the way that we think about this, if you think in terms of y, then you're talking about the limits of y and then the rightmost y function minus the leftmost y function, and you integrate with respect to y. Now if you think in terms of y, you're always going between the same two functions. Okay, so this is an easier way to do this. Okay, the only thing here is that you need to rewrite the functions in terms of y. You need to make x subject if it is not the subject. Okay, right. So now let's finish this problem. So 0 to 2, y minus y square minus minus plus 2 dy. Now if you integrate y, it's y square over 2. If you integrate y square, it's y cube over 3, plus if you integrate 2, it's 2y, going from 2 to 0. Now substitute 2. So 2 square is 4, 4 over 2 is 2, minus 8 over 3 plus 2 times 2 is 4, minus if you substitute 0 here all the way, it's going to be 0 for y, right? And then if you simplify, 4 plus 2 is 6, 6 minus 8 over 3 is 10 over 3. So this is unit squares 10 over 3. And remember in the last video when we used a different approach, we also got 10 over 3, right? So no matter which technique you use, you end up with the same answer because of course the area doesn't change. It's just the methodology that you use is different, right? But you should end up with the same answer. So that's the idea. This is called partitioning using y-axis. We find the area by partitioning the y-axis. Okay, not using the x-axis, but we're using the y-axis. All right, so the basic idea is now instead of x limits, you are thinking about y limits, y1 to y2, bottom y value to top y value, and then here the right y function minus the left y function, and integrate with respect to y. But when you need to find the right y function and left y function, if x is not the subject, you have to make the subject of the equation to be x and write the function in terms of y. Okay, right. So that's the idea. So in the next video, I'm gonna actually solve several examples from this new technique. Okay.